Yes, together with us today is actually the main act. So Sherif Abdelwahab from Microsoft. He is a principal software engineer architect at Microsoft and is basically defining the architectural direction for the multi-agent physical AI platform, which spans the edge runtime, messaging, AI lifecycle services. And he actually holds a PhD in edge and IoT systems and has already several patents under his belt in distributed edge computing. So I don't think there could be a better person to talk about all of this than him. So Sherif, thank you. And yeah, the floor is yours.
Okay, thank you very much for having me today. So a quick disclaimer first that I'm going to present thingctx. It's my personal project and it's open source under Apache license. This is not really a Microsoft product, nor a Microsoft position. It's entirely my personal work. So the thesis here is actually in the title. So that agent integration these days are effectively documents. And that thing description, which is the main concern of this group, is already the integration that agents are needed. An agent, it's basically a document that the agent reads, not really a server or a middleware that you run. This group knows Web of Things quite well, so I'm not really going to explain what TD is, but I will show you how what a TD becomes inside an agent loop, and where the opportunity for an open spec work might be. But first, 1 minute on why this matters now. So next slide, please. So the Web of Things started with one simple idea, that we have a thing description that describes itself well enough that any program can actually use it. And essentially, that program reads the description and acts on it. So for years, what I have observed is that the readers are pretty much like browsers or gateways or other things that talk to each other. So the idea that to have one single description that describes a system remain pretty much like theoretical on paper. But if you notice that this pattern of having a description of a system is quite not new. So it started with XDR in some microsystems, then WSDL, then OpenAPI, Protobuf, GraphQL. So, and the caveat here is that the description of a system always lives longer than the code that it actually reads it. And what is really new today is the new readers for these systems, which is the agents. A language model can take a thing description it really has never seen before and drive the system behind it. Nobody wrote those TD actually for a model, but they can actually work anyway. And the idea to have a thing description for a system actually have a reader that immediately act on that. Next slide, please. So how do agents reach systems today? The answer is that we build actually every integration by hand, one for each system. And sometimes it is an MCP server that you deploy, keep running, manage all of the credentials for it. And sometimes it's just a tool definition, or what they call today skill. But in all of these cases, someone needs to write each integration by hand. And if you have N systems, you will end up with N integrations, managing N kind of integrations, different type of integrations. And so for a fleet of devices, so this means that we have one integration even for, I don't know, a light bulb. So this is really the world we are in today. And ironically, WoT is not necessarily part of it, although that it is well positioned to describe these systems pretty well. Next slide, please. So, but let me take a step back and try to answer one single question, like why does everyone today build these integrations by hand? And the simple answer is that the agent and the systems do not really have a shared contract. So there is no agreed way to say what the system does, who is allowed to call it, how to reach it on a transport, or what kind of events it emits. So we end up having every single team answers those 4 questions again and again by hand. And the contract that we were talking about ends up in code that is wired in the server and ends up living there. But here's the turn, is that a thing description actually answers all the 4 part of a contract for them. So the thing description has the typing, it has security definitions, transport definitions, and events. So in other words, like, we already wrote the contract that an agent may actually take without rebuilding that. It just we didn't really have a mechanism for it to read it yet. So in the next slides, I will show you how close a TD actually already is, being the agent tool itself. So next slide, please. So if you look into a thing description, like, everything we need is already in the TD. The typed actions, the forms, the security definitions. So the description on the left-hand side of this slide and the tool model on the right-hand side are pretty much the same object. And let me define 2 quick terms here, is that in case they are new to anybody. So a tool call means that a model outputs a name and a JSON argument, and there is a runtime that's going to execute that. And once the runtime executed, the results come back to the model. And an MCP, in fact, is just a protocol for delivering tools to an agent that you cannot hand them to directly. But the MCP does not define the contract itself. On the next slide, I will show you why the TD fits with really nothing added in the middle. So next slide, please. So when you put a TD action and an LLM tool really side by side, they have pretty much the same shape. Both have a name, a description, an input schema for the typed input schema, and the TD already has all the 3. So the form then carries the rest. It defines how to reach the system over which transport, and the security definition, how to authenticate to it. So here is what happens on a call. So thingctx, which is the library that we're talking about today, takes the arguments from the model and fills the URL template. So it uses the method from the form, and it builds the body for the tool. And then it applies all the security scheme at call time, which means, even from a security perspective, that the secrets and credentials themselves never actually lives inside the TD and can be handled securely in a unified way. So the typing comes from the input schema, the transport, and the security comes from the form. And none of it is really coded by hand anymore. It's actually just described in the TD. So now there is one claim I just want to make carefully. This kind of projection or resolution is pretty much deterministic. So the same TD always produces the same code. So if you give me the same TD, I will just have exactly the same tool spec. And that's exactly what makes it possible to write this down as a specification. So instead of it living only inside my library. So if we have a specification note that says, this is how a TD action should be mapped to tool specification, now we can have like a kind of a portable way of doing these kind of projections. However, on the other side, the naming, like in this example, github.create issue, requires a different story, and which I would like to explain it a little bit in the next slide. So next slide, please. So on the left side is the part that is pretty much solved, is that we can have a deterministic mapping between the TD and the tool codes. So the input schema maps to the parameters, the form maps to the call, and the security maps to authentication. It's pretty much deterministic, so any conforming consumer will get a repeatable results, dependable results. And this part is what already written down. On the right-hand side, this one is quite open question, and this is related to naming. So TD today, the only promise that it makes is that names are unique inside one TD, one thing. But an agent will actually flattens many things into a single list of tools, and specifications say nothing really about a situation like this. So in thingctx, my naming, I have chosen a thing.action as a default, but it really can collide. So this is a kind of a gap, and honestly, it is the best reason why this group may be interested to write down together as a note. And there is one more open question to this. A tool list is actually shows the model only a part of the thing. And there is a question like how much of a thing or a TD should actually reach the model is in its own an open question. So we do have a collision naming that every implementation would need to either find a way for it, or we have a note that describes it. And the other one is that how much at TD we can actually promise to reach the tool and in an implementation. Next slide, please. So now one can actually fairly say that, okay, fine, it can work on your own files and on your own TDs. And here is a test that I wanted to do to actually see if thingctx can work with TDs that it has never seen before. So I've taken Node.WoT, which is a reference implementation, produce a TD, and thingctx consumed it cold actually without any coordination between Node.WoT and thingctx. And I've done exactly the same with Ditto, which publishes its own DTs for digital twins. And I was able to write 0.42 to a digital twin, to Ditto twin, and read back 0.42 from Ditto's API without any previous coordination with Ditto. Like I've never even seen the details of the code. And neither of those projects have ever been integrated directly or coordinated with thingctx, which is just new. And the only contract between them was the TD that those tools have written already. And this is the power of the web in the Web of Things definition, that specification. And both examples run from in the repo. You can check this yourself, and instead of really taking my words for it, and you can find that examples in interop folder in thingctx repo. Next slide, please. So the mapping works, and the next question is, how does that reach the agent? And there are a couple of two cases in practice. The simple case is that you actually own the agent loop. There's no bridge at all that you really need in this case. And thingctx is just a library that you consume in your agent process. It hands you the tool specs. You pass them to your model through something like Light LLM or VLLM or even the OpenAI SDK. And the model picks a tool, and you can call invoke, which is a function in the library. And there is no server. There is nothing actually to deploy at this point. So when you control actually the loop, the mapping alone is sufficient. And the bridge on the next slide is only for the cases where you cannot really do direct tool calling in the agent, and the agent has a mechanism for integration that you do not really control. So next slide, please. The second case is that you have a closed agent that only takes integrations through basically doors that the vendor of that agent opens for you. One of those are pretty common with MCP and the skills. So thingctx ships one generic MCP server that serves a whole entire registry of TDs. And so you can think of it like just one single process, one single bridge that you manage for the whole entire fleet, not actually a server per system. But MCP, in fact, is not necessarily the only door that we have. The same TDs can also become invoked from a CLI with one command per action. And a skill, which is just a markdown file, can drive the CLI. It's the same fleet for TDs, and there's no server at all. And to be clear about the skill is still a file that describes what needs to be done, but it only says what to do. It still needs a runtime to do it. So thingctx still does the transport and the authentication using the TDs. And the skill in this case is pretty much a recipe, but thingctx is still the runtime underneath that recipe. So in closed agent case, the door is pretty much a vendor choice. And MCP today maybe scales now or something else tomorrow. But the integration remains the TD documents. And it does not change when these kind of doors or these kind of ways of integrating with the agents change. So one single aspect here is events, because events like have a very specific shape in TDs. And it turns out that they also survive this integration too. So in a WoT, WoT subscribe action becomes an MCP resource update. And in thingctx, I buffer it so that burst of changes don't really get lost. Next slide, please. So far, you have seen a mapping and the bridge and some few extras. And a fair point at this point is that which of these actually needs the standard? And I have been thinking through this, and I think the answer comes in 3 layers. In the first layer is the mapping itself. So you need a TD, and you get a tool. It needs nothing actually new from the standard. And it's the only part I'm asking to write down is one mapping for this TD to the tool calling. The second layer is an optional extension, which thingctx already have. Things like approvals or prompts that you find in MCP servers. They use WoT own extension points, so they are not really a new spec change that's needed here. And layer 3 is not WoT at all. It's not Web of Things at all. The event buffering, for example, is just handlers and MCP to work around MCP limitation. So it's kind of a consumer side handling if you have MCP or skills or something else, so that you work around their limitations. So nothing I have shown so far says that the standard has any limitation actually for this to happen. And the main headline is that the standard as it is today really gives you that agentic tool calling that agents need. Next slide, please. So I wanted to touch a little bit why we may need a node, not just like a mapping that lives in a repo. And the reason I've been thinking through is that TD is a stable thing here, is a stable definition of the system. And the mapping is a layer underneath that can actually keep improving or evolving. So if the MCP spec changes, but compare this to MCP. So MCP spec changes, like every server authors need to rewrite their server if they have breaking changes. But in the mapping case, even if the mapping changes, nobody touches the TD, which defines what the system needs to do, the integration layer. A TD you write today stays valid even if we evolve those mapping. But there is also a second reason why we need a node. If the mapping only lives, let's say, in my repo in thingctx, it becomes a convention that just one single project controls. And when I think through that, it is quite the opposite of what Web of Things TD is supposed to be in terms of neutrality and interoperability. So a node keeps it neutral. And honestly, I would rather implement something that is specified here over like my own mapping, even if it just works and doesn't really break anyone's TD. Next slide, please. So here is where things are and what's actually open today. You can install it with a pip install, just one single command in Python, and then point it at something that you already have tonight and see a model like an agent driving a system that is described by a TD. And beyond that, there is probably a TD worth writing for a system you already know well. If you write it once, every single agent that reaches that system can read it. And the open problems are the ones that this specification group is for, and things that we described, like naming across a fleet, output schemas or events over MCP. And also, if you read the mapping document that I have in the repo, and I have a reference for it right there, you can help by telling me where it might be wrong today. And that's honestly one of the most useful things the community can give a project like this. And there's one last question that I would like to put on the table. If a model can read a TD and act, can a model actually also write a TD? So if you already have a messy system, can an AI write a TD for it? So we already do this part, kind of can do this part today. So if I take like an open API specs, we can actually write a TD for it. But the hard part for this is trust. So how can we have a trust layer? Because an auto-generated description becomes only safe if you check it against a real system. And this is also another open problem that I'll be happy to dig into with the community later. So to close, a TD, as it already exists today, is an agent tool. And writing it down, how to consume it worth doing together. And that's pretty much it. Thank you very much.